I have approximately 45 minutes, 40. How much time, Nancy?
I think 45 minutes is good enough. If you can arrive to the rock analysis, till the rock analysis should be best. And their predictions as well.
Okay. So this is the environment of Orange. Orange is a very powerful tool because you can run machine learning algorithms, you can train your algorithms, you can produce results, and you produce forecasts without any knowledge of Python. You do not need to learn Python to perform the analysis that you're going to see now. So you basically have this graphical user interface with all these nodes that are interconnected. And it is easy for someone that is new in machine learning to use it and basically understand what's going on and how we train these models. Of course, you can also, behind the scenes, behind these nodes, of course, Orange runs Python code, okay? So this is my pipeline. It is as already designed and set up pipeline that I use in my courses for my students, so they do not have to start building this pipeline by themselves, because it takes a lot of time to understand how and why you must connect, for example, this with that here and again this with that there. So this is the pipeline to perform classification. We start with the first node, the file. Here, if you double click, you select the file that you want. In this case, classification of data card. This is my file. And when you open this, when Orange reads your data, you can see that already recognizes that this is your dependent variable. Okay, this is the target. So this is called target here, the no pay. So this variable is 1 whenever the customer, whenever we have a bad customer, they do not pay, and it is a 0 whenever we have a good customer. If it is not automatically selected like this, like a target, and it is selected like a feature, a normal variable, then you can do it by yourself, right? You can click here and say, okay, Orange, this is a target variable. Same thing with all the other variables. Customer here is not a variable, because it is not it's not a variable because it is just the customer number or the name. Of course, for anonymity, GDPR and all that, we have only the customer's number, not the name or any other identifying information. And so this just distinguishes the different customers. It's not a variable that we can use for forecasting, and this is why it is marked as meta. Okay. So we can differentiate the different customers. I press apply to load this data. You see that dynamically now Orange has started already training the models, but we are going to go step by step. First of all, after we upload our data, I always use the color node, and this node is important because, as you can see here, we can color our observations for categorical variables like this. So these two variables, employed or owns a house, are categorical variables. 1 means the person is employed, 0 is unemployed. Owns a house, 1. They own a house, 0, they do not own a house. So depending on the type of variable you have, either discrete variables, this categorical, we have 2 categorical variables and 2 continuous variables, numerical variables, you get Orange paints the data, so it is easier to identify patterns. You're going to see that is always nice to use the colors for illustrations. So after the color, as I said before, we need always to graph the data, and this is what we're going to do in a few seconds. I go to this branch here where we can see our whole data set. Okay, as you can see, this is our dependent variable, no pay, with the different values, 0 for a good customer, 1 for a bad customer. This is the customer, the meta variable, the customer number, 1 to 100. I use only 100 observations so that the models train efficiently and quickly here. We do not want 1,000 customers or 10,000 customers so that it takes, I don't know, 10, 15 minutes to train. And you also get a visualization here of the balance, the numerical independent variables, balance and income. So this person here, this exact person has a balance of 11,000 euros and an income of 40,000 euros per year. You get the colored bars. The color blue, it means here that this person is a good customer, unlike this person. This person here, which is marked as red, so this person is a bad customer. So this is only for illustration purposes. The data table. Also, we have for illustration the feature statistics. Let me, because I selected only this, so I get restore original order. Okay. Let me, how can I unselect this? Okay. 1 second, I'm going to explain here. Okay. Because I selected that person, I got in this node only that person data. So now I have my full data set. As you can see here, we have the so-called descriptive statistics. You can see that the color here is for no pay. So whenever you see someone with a balance, these are low balances and high balances on their accounts. You see that people with low balances, they are blue, which means that the no pay variable, the dependent variable is 0, so they are good customers. But when you start with balances from this point and to the right, higher balances, the people start to not pay their credit cards. They start becoming bad customers. The same information here for the income variable. Now you see that no matter what the income is, low income or high income, there are still a lot of people that do not pay their credit cards. So income is not a variable that can clearly distinguish between the two kinds of customers, the bad and the good customers. Same thing here with the employed, whether they own a house and so on. So this is for illustration. This feature statistics. Next, we have the scatter plot, where we can get a visual illustration of the data. Remember, this is exactly the same data set that I showed you before for the credit cards. Of course, it makes sense. You can select which variables to put in the X and Y axis. Of course, it makes sense to use the numerical variables, not. Let's see what happens when I put the employed, unemployed. It's not that informative. Not balance and income. We can see the same type of graph. We can play here with the symbol sizes and everything, whatever you want to do. You can show grid lines to distinguish between the different individuals here. So, okay, this is again for illustration. And finally, in this first exploration of our data set, we have the correlations. Of course, correlations are defined only for numerical variables. In this case, we have only two numerical variables, balance and income, and we see that their correlation is minus 0.046. So they have a low correlation. And this is important because if we have let's say 10 different numerical variables in another data set, and some of them are highly correlated. Usually what we need to do is to exclude the variables that show high correlations, because we have multicollinearity. Okay, so basically if you see correlations higher than 0.8, absolute 0.8, it may be 0.8 or minus 0.8. So absolute 0.8 or absolute 0.9, higher than that, we usually exclude one of the two variables that are highly correlated. Okay, now this all is a pre-processing step for our data. We just take a look of our data and see how they generally look with the colors and everything. Now let's go to the main branch here, where we start building the algorithms and training our models. Now again, here I have the data table, because we need the data to proceed. Okay, so this is the same node. I have it 2 times for different reasons. This is an important node now, the select columns node. When you double click, you get all the variables, and automatically Orange tries to understand which one is the target variable, which ones are the featured independent variables, and which one of the original variables are just meta variables or just informative variables that are not going to be used in the training process. In this case, they are correctly identified. Maybe I can take this customer and put it here as a meta variable, or if you get a data set that looks like this, okay, nothing is selected by Orange, you can do it by hand. Okay, I know that no pay is my target variable. I highlight it and then either press this to go as a target, or I can click, drag and drop here. So my target is this. All these highlighted are my independent variables. Drag and drop here, and this is the customer number. Informative variable, not an independent or dependent variable. You get the information here that you have 100 observations and 4 independent variables. You can press now here to send these variables. As you can see, it is sent through this pipeline. All this thing here is called an ML pipeline, machine learning pipeline. Or you can just click this, so anytime you make a change here, automatically Orange sends the data to feed the models, whatever is better for you. Okay, this is for the select columns. Now we go to the next node, that is the data sampler. In this case now, the only thing you need to do is, this is the place where we define 2 different subsamples of our full set of data. Here we define the training and the validation data sets. So usually what we do in machine learning is that, let's say in this case, as you can see, we have a set, the whole data set includes 100 observations. What we do is separate the training set from the validation set. The training set usually is like this, 80% of our original data set. So in this case, it is 8 observations, while 20 is the validation set. Of course, we can play with this. We can make it 70%, 74% in this case, or whatever. Usually what we select, depending on the number of observations that we have, is 80%. So from now on, what I just instructed Orange to do now is to just use 80% of the original data set to train the algorithms. So the algorithms that we're going to produce, the models that we're going to produce, only see this 80% of the data set, and they never see the remaining data, the 20%, 20 observations. Why we do that? We do that to see how well our trained models are going to perform on this out of sample unknown set, the 20% of the remaining data. Because if you have a very good model with 90% accuracy in the training set, but when you try new data, either this 20% or any other type of new data, and you get 60% accuracy, then it means that you have overfitting. Your model is very good at predicting the specific sample that you have at hand, but it's not very good for any other data set. Okay, so this is why here in the data sampler we separate these two samples. Also, what is important here, we have the option to create replicable sampling, which means it is a deterministic sample. This means that every time I rerun my algorithms, I change something, I close orange and I reopen orange, the same exact observations are selected for the 80% and the 20%. Why we need this? We need this so that because if we do not select this, because anytime we rerun this data set, Orange is going to randomly select 80% of the data, so we're going to have slightly different results every time. It is not bad because they're randomly selected, but in this case, we impose the same randomness every time we open the Orange or rerun our algorithms in order to make our comparisons easier between the different models. Another important option is to select to stratify the two samples. This here. This means that to stratify means that we keep the same proportion of zeros and ones, so good and bad customers, in both the training and the validation set. Okay, because if in the original data sample, we have, let's say, 30% bad customers and 70% good customers. And since we select the training sample randomly, okay, we may select all the bad customers in that sample and no bad customer in the validation sample. This is why usually we need to stratify our sample. Again, here you can see that from the information here means that from the original 100 observations, now you have two different data sets, the 80 observations that are going to be used for training and 20 observations that are going to be used for validating our trained models. What else here? You do not have to touch anything else here. You can press this to create the two samples, or automatically it is created by Orange. As you can see now, it works. It trains the models. So this is the data sampler. This node here. Let's close this, and now let's move to the models. The actual models that I have included here in this exercise, in this empirical example, is the neural network algorithm, the logistic regression, which is most of the time people in machine learning, they call it a machine learning model, but it is not a machine learning model, right? It is a classic traditional econometrics model, but for some reason they include it in the machine learning models anyways. So we have neural networks algorithm, logistic regression algorithm, decision tree algorithm, the gradient boosting algorithm, and 4 types of support vector machines algorithms. The difference between those 3 types of support vector machines algorithms is that we have here different kernels. As you can see, I have the SVM with the linear kernel, the SVM with the polynomial, RBF, and sigmoid kernel. Remember, the kernel is the trick where we project the data in higher dimensions so that they can be more easily separable between the two or more classes that we may have in our data problem. So these 1, 2, 3, 4, 5, 6, 7, 8 models, these are this is the total amount of models that we are going to train here. These are some of the most powerful algorithms that exist today, and we expect to get good results. Usually in machine learning, we train more than one algorithms. We can perform the same analysis with just a neural network, right? But usually we try more than one algorithm because some algorithms are better in some problems and some other algorithms perform better in other problems. This is why we use a variety of ML algorithms. If you now, for each one of these models, let's double click this, the neural network, you get this. So here you get some parameters of this specific model. The parameters are that the neurons in the hidden layers. Yes?
Can I come this? Could you please only focus on the logistic regression and trees as well, because the students were not going to see anything like this further. So just to save the time. Yeah, logistic regression and the trees as well.
Okay. So for the logistic regression, it is very simple. The only parameter that we have here is this regularization type. The default one is Ridge regression L2, but you can try also this one, and you get different results. It is perfectly fine to just use the default values here to select the best algorithm, and then let's say you find out that logistic regression is the superior from all these 8 algorithms, and then you can fine-tune that algorithm. If you find that logistic regression is the best, produces the best results, then you can also play with this, okay, or this to slightly improve the forecasting results. Also for the trees, decision trees, okay, now you have the minimum number of instances in the tree leaves, do not split subsets smaller than. So you have another set here, 1, 2, 3, 4 extra 4 parameters. Here you have the default values that you can play after you train the model, if you want to. If you get a model that is adequately accurate, you do not necessarily need to play with this any further. Okay, so another thing you are going to see here is that I also have this stacking model here. This stacking model, what it is not a separate machine learning algorithm, but it combines the results from 2 or more algorithms. In this case, I connected this node to those 3 algorithms, the neural network, logistic regression, and decision trees. So this decides here forecasts based on the votes that it gets from these 3 algorithms. So if these 2 say that this customer is going to be a good customer, and this one says that this customer is going to be a bad customer, the votes are 2 to 1. So stacking produces a result of this is a good customer. So the target variable is 0, and so on. So this is a voting mechanism between the different algorithms. Of course, I can connect this to all these 8 algorithms, and then 8 algorithms vote for the final result. Now, let's move to this very important node now. These are all our algorithms, the pink ones. Let's move to the test score. Here, if you double press this, let me arrange better the numbers there. Okay. So what we see here, okay, what are the important parts from this node? First of all, what you see here, forget this, it is not needed. Don't confuse you with, I'm not going to confuse you with this. The important part is this one here. Here, what you get is the specific forecasting metrics for all the models that you train. As you can see, we have all the models here, okay, that we trained, and we have various forecasting metrics. This test means how much time did it take to train this model. It took 0.03 seconds for this, and so on. So this is not important. Now, the important parts are the area under the curve. We're going to see that when we talk about the ROC curve here. The higher the number, the better the model. This one, which is CA, represents classification accuracy. So this is the total accuracy of our models. And sometimes you can select the recall metric or sensitivity, two different terms for the same metric, sensitivity or recall, which is the accuracy that we predict this class here, class 1. So all these metrics are relevant to how well we predict class 1. We can select the same metrics for class 0, or we can select the average between the two classes. Let's say that we're more interested in the bad customers. So based on the evaluation results for target 1 and the area under the curve, if we press here, we sort the different models. And as you can see, let me see, okay, the best model in this case is, according to the AUC, is the logistic regression, because we have an AUC of 0.956. The worst model is the tree model with 0.913. It's still good, but in comparison to the logistic regression, it is not that good. If we select this metric, the recall, then we can see that according to the recall sensitivity, the best model is SVM linear. So this is the usefulness of this table here. Another important part of this node, the test and score node, this node here, is this one. Here we instruct Orange to perform cross-validation. And we instructed to separate our training sample, so the 80 observations that are left. Remember, we separated 80% and 20% as out of sample. So for the 80 observations that are in sample, I now instruct Orange to use cross-validation, creating 5 folds of that 80% of that 80 observations. So 80 divided by 5, it means that we have 5 folds with 16 observations for each one of the folds. I think your professor, Nancy, will explain to you better. She's going to have more time to explain why we perform cross-validation. Long story short, spoiler alert, we do that so that we do not have overfitting. Okay, so when you select this cross-validation, and usually we use 3 or 5 folds, the number of folds, the results that you see here are the results for training. These are the results for the models that are now already trained. It took this time to train, and these are the forecasting results. If you want to see now the results for these trained models, when you feed them, the model is already created. You have a specific equation with specific coefficients and parameters, and now you need to feed it with new data and see how well it performs. We are going to feed it with the 20% that we left aside. They did not take part in the training process, and see how well this model performs. To do that, we go to this test on test data. This means, okay, these are the trained models. Now pass through this trained models, the 20% of the data that were left aside. I click on this and now it calculates the metrics again here. And as you can see, now we have the metrics for the part of the data set that was left out, the out of sample data. The only things you need to play with here in your empirical work is this: either press cross-validation with, let's say, 5 folds to create the in-sample, the training set, the training set models and forecasting parameters, or press, after you train the models, you press test on test data to see how well it performs in the validation set, the out of sample set. What I have next, okay, now since we are in a classification problem, with these models, we have the confusion matrix. The confusion matrix is a very powerful tool here that illustrates how well everything is, how well the models work. Okay, what we see here, first of all, we select which one of the 8-9 models that we train. Let's say we select the stacking model. Okay, now it provides here the number of instances we see on the main diagonal. This one, this is the main diagonal, and this is the secondary diagonal. The blue ones are the correct classifications. So in the rows we have the actual cases, okay, the actual, whether the customer was actually a 0 or a 1, a good customer or a bad customer. And on the columns, we have how our model predicted those customers, whether it predicted them as a good customer or a bad customer. So, for example, for these, we have only 20 instances because I have selected here, okay, because I have the test on test data, I have the 20% of the data. Now you're going to see the results for the it is still training, as you can see. Come on. Okay, now it's done. So now you see the results for the 8 observations in the training set. So now out of those 8 observations, the actual number of good customers is 51. So we have 51 good customers and 29 bad customers. Out of those 51 good customers, our model predicted, this model, the stacking model, predicted as good customers 46, and 5 of the good customers were predicted. So we have a false prediction. 5 of the good customers were predicted as bad customers. For the ones that have ones, so they are bad customers, the total number is 29. 23 of those were correctly identified, predicted by our stacking model as bad customers, but 6 of those were classified as good customers, and this is incorrect. So these are the correct classifications: a 0 that's classified as 0, and a 1 that is classified as a 1 in this main diagonal. And on the secondary diagonal, we have all the misclassifications of our model. You can also, these are the number of his instances, as you see here. So 46 people are correctly classified as good customers, but you can also, to compare different data sets, you can also use this, the proportion of actual. Now you get percentages. You see now you can interpret this that 90.2% of the good customers were correctly classified, and 79.3% of bad customers were correctly classified. And of course, these 9.8% of good customers were wrongly misclassified as bad, and these bad customers were 20% of the bad customers were misclassified as good customers. So this is why we use the confusion matrix. Again, the confusion matrix is only relevant to classification problems. Now let's go to the ROC analysis, the ROC curve. Now, what is the ROC curve? The ROC curve tells us how well the model predicts the selected class. Here we select the class 1 or class 2. We have different ROC curves. So for class 1, that is the class of interest, I want to distinguish the bad customers from the good customers. So the ROC tells us how well the model, the specific model, in this case, the stacking model, because this is the one highlighted. I can also include this, that, as you can see, a lot of ROC curves for the different models. Let's concentrate on one, so it is easier to understand. So this is the ROC curve for the stacking models. A little bit of background. We may classify with the model customers as either 0 or 1, but actually the models, what they spit out, what they produce as forecast, is a probability that each specific observation is class 1. Okay, so they provide a probability that each specific observation belongs to class 1. It is a bad customer. So if it is a high probability that it's a bad customer, we classify the specific person as a bad customer. If we get a 0.01 probability that this person is a bad customer, we classify it as a good customer. But to decide this, we must set a threshold. Okay, and the obvious threshold is 50%. Every time I get a probability higher than 50%, then that person is classified as a bad customer. Every time I get a probability lower than 0.5, 50%, I classify this person as a good customer. Now, we can change this threshold, okay, in order to be able to increase our accuracy. And the way we interpret this ROC curve is that starting from the top right, here the threshold is equal to 0. So what that means that for every observation, if the threshold is 0, so everyone is going to have a predicted probability of being a bad customer higher than 0. So everybody is predicted as a bad customer. So this is not a very good model, of course, right? Here, everybody is predicted as a bad customer, which means that the sensitivity, the ability to distinguish the bad customers is for this model 1. So 100%. So 100% of the bad customers are identified by this naive, basically stupid model, because since we classify everybody as a bad customer, of course we can identify everybody as a bad customer. It's a similar example would be if we want to classify people in our customers as men and women, let's say, and we classify everybody as women. We say everybody is a woman. Okay, this means that we correctly identified all women as women, but we totally misclassified all men as women. Now, this is obvious here because if you do that, if the threshold is 0, the class 1 is, your accuracy in class 1 is 100%, but your accuracy, this is 1 minus specificity, or also called the false positive rate. You have a false positive rate for the other class, the class 0, of 100%. So, okay, you correctly classified everybody that is a bad customer, but you also have a false positive rate of 100%. You misclassified all the good customers as bad customers. So basically, you do not accept any application for a credit card because you classify everyone as a bad customer. The opposite case is where when we move from this one where the threshold is 0, in this point here of the ROC, the threshold is 1. In this case, I think yes, as you can see, now orange tells me it doesn't stay for long. Orange tells me that the threshold here is 1, which means that I'm going to classify as a bad customer only the people with a probability higher than 1. Of course, nobody has a probability higher than 1. It is a probability higher than 1 and less than 0 is not defined. So nobody passes this threshold of 1. So in this case, in this area here, nobody is the sensitivity of the model is 0. No bad customer is correctly identified. And this is why here we have a 0. And since basically everybody is identified, classified as a good customer, this means that I also have a false positive rate or a false alarm of bad customers equal to 0. Okay, because all good customers are classified as good customers because nobody is identified whether they are good or bad customers. Nobody is identified as a bad customer. But between the two extremes, threshold 0, threshold 1, we have here the threshold, you see, default threshold 0.5. When you select this, immediately orange shows you where the point of the threshold 0.5 is. You see here 0.602 because automatically orange shows the observation that has a probability closer to 0.5. So this is the observation. I think it's this. Yes, this one. This is the specific observation that has a probability closer to 0.5 that I set as a default threshold. So this is my model. If I use the default threshold of 0.5, which means that this model now has a 0.76 true positive rate. So the sensitivity is 76%. Out of all bad customers, I'm able to identify 76 of them. Okay, and this also creates a false positive rate. If this is the point, also creates a false positive rate of, I don't know what is this here, 0.10%. So 10% of the good customers are misclassified, we have false alarms, are misclassified as bad customers. So this is my model with a default threshold. I can also choose a different threshold. If it is very important for me to identify all the bad customers, I can move, for example, here. So in this case, setting a threshold of 0.187, this. Now, my sensitivity to identify the bad customers goes up from 76% to 93%, but also there is a trade-off here, but also the false alarms, the false positive rate goes up from 10% to 20%. So now 20% of my good customers are identified as bad customers. So it's up to me to decide which threshold I'm going to use. Usually, we are fine with a 50% with a 50% threshold. Nancy, how are we about time?
Professor, we can finish because the students, they are not going to say anything else other than this. So we don't have to explain what is the high, what is the other one? I don't remember the future importance and all of these details because they don't have time to we don't have time to analyze everything. So I think so we can finish the session. You can finish if you want. Now is a good time for you after 3 hours. After this 2 hours, 3 hours, whatever it is. I don't know if the students have any question for you at the moment. The most important part that I want to say is just the orange could be, it's very simple. If you start playing a little bit with the data and everything. You need to clean the data first. Yeah, the question is, can they clean the data from orange? And if so, could they clean the data before start doing anything based on the algorithms?
Okay, so the answer is you should also try to clean your data, which means inspect your data. For example, you can use the pre-process here in Orange. And you can do a lot of things. You can, where it is, you can select here, impute missing values. So you either average the value where there are missing values, or you replace with a random value, or you remove the whole row, the whole observation when there is a missing value, or you can do a lot of things. So of course you can, this is true, you can clean your data using Orange, but to tell you the truth, it's much easier to just use your Excel to inspect the data. And then you can, if you need to perform some of these processes, randomize, normalize, or whatever, then of course it is very easy with Orange to perform these pre-processes.
Another question, Professor, is should the students follow exactly this pattern by design the paperling like this? Or could they just randomly select which is going to be the second step, which is the third step, which is the fourth step, so on?
What do you mean by steps?
I mean that the way that you saw that is that the first step is obviously to open and down to upload the file. The next one is that the data tables you have provided, the discrete analytics, so on.
Okay.
Can they do different steps before start looking this? For example, can they jump to train the model, to split the model first, to split the data, or they should follow exactly?
Okay, no, you have to follow these steps because they make sense, right? First, you upload the data, then you have to select the independent and the dependent variables. Then, in this case, you split the sample, and so on. So this is the best way to proceed. It's logical, it's efficient, and it's the best way to proceed.
Do you have any questions? No. But based on the cross-validation that you shared before, they can skip also the cross-validation, isn't it? They don't have to do the cross-validation because we didn't discuss about this. We will not discuss as well. So they can just train the model the whole 80%.
Yes, you can do this test on trained data. Okay, you can, if you press this, then now your model is trained on the whole data without cross-validation. As you can see, validation now is not selected, so it's there's no cross-validation. But as you can see now, you get models, guys, with 100% accuracy, which means this is overfitting. We have overfitting. They look nice, the models, but it's fake because it's overfitting, because we did not perform cross-validation.
And you can see that they change. Okay. I think they do not have any other question. I would say thank you so much for attending to this. Let me stop video recording.
Okay, my pleasure. Nancy, I'm gonna send you the presentation, and maybe if you want the pipeline for the